Hello, everyone. Welcome back. It's time for some more organic chemistry. We are in Key Concepts Unit 3, Part 2. We already got started in this section. This was wrapping up the alkyne reactions, the carbon-carbon triple bond reactions. So now we're moving on to another functional group, alkyl halides. And let's see, we actually started that by reviewing, oh, I forgot to cut and paste it here. But we reviewed I think a couple reactions on how to make alkyl halides. You know, carbon-carbon single bond molecules, alkanes containing halides. Okay, and one of the last things we talked about was the order of stability for radicals, and it follows the same order of stability for carbocations. Previously, we discussed how tertiary carbocations were more stable than secondary, more stable than primary, right? So we covered this section right here before. And then we just introduced in the last video how it doesn't matter whether this carbon's positive or if it's a single electron, a radical, it follows the same order. And then we kind of put more pieces at the ends of this, this trend here. We said that, hey, if you have a pi bond adjacent to that carbon with the radical or the carbocation, a pi bond, carbon-carbon pi bond, or some other pi bond, you get resonance stabilization. And even though this free radical here is primary, which would put it way down the other side where it's not supposed to be stable, because of the pi bond adjacent to this radical, we get resonance stabilization. There's the resonance arrow, double-headed arrow. And what happens is the pi bond just kind of rolls over to the other side. And then the carbon that used to have a double bond, this carbon on the left, no longer has a double bond, it's missing a bond. So now it's positively charged. And the same pattern here, if this radical begins on the right side in the resonance structure, then the radical will be on the left-hand side and the pi bond will be on the right. There. So I just copied all these atoms. Remember, that's the pattern for resonance structures. Resonance structures, you cannot move atoms. CH2, CH, CH2, same set of atoms. All you can do is to move electrons. That's all you can do. And then in a benzene aromatic molecule, there's 3 pi bonds. And as long as one of the pi bonds is close to the radical, you also get resonance stabilization. We won't discuss the aromatic functional group until next semester. So, but I just want to give you a heads up, hey, it also enjoys resonance, it's very stable. And oddly enough, if you put the carbocation or the radical directly on the carbon that's involved in a double bond, that is just really unstable. Nature says, no, that is a bad idea. Okay, so that's where we ended the last video. Today, we're going to exploit this trend. So what's the most stable radical or carbocation? It's the allylic or the benzylic, right? I'm not going to do the benzylic today. We're going to look at the allylic radical. And so there's a reaction that makes free radicals very gently so that only the most stable free radicals can form. And that would be the allylic radical. And then we're going to put a halide where currently there's a radical. In fact, not just any halide, we're going to put bromine. So that gives us our first reaction today, allylic bromination. Can you get the whole thing on here? Almost. All right, allylic bromination. Let's start with propene, carbon-carbon double bond. We use that molecule to describe a lot of reactions in Unit 2 involving alkenes. So here they are again, but in the context that, hey, you can take an alkene and turn it into an alkyl halide. How do you do that? Well, you add this molecule that you can just simply abbreviate as NBS. NBS stands for N-bromosuccinimide. Maybe I'll put it over here. NBS looks like this. It's got a nitrogen and 4 carbons in a ring. And there's a double bond O on either side of that nitrogen. And nitrogen makes 3 bonds, right? Yeah, remember the quick little acronym or memory aid, that's supposed to be an N. HNO, H-O-N-C, honk. Honk the horn of your car. 1, 2, 3, 4. Nitrogen makes 3 bonds. Yes, so where's its third bond? It's to a bromine. So that's a bit unusual, nitrogen bromine bond. It's unusual because it's fairly weak. The chemist would say it's labile, it's not very stable. Stable enough to store in a jar, but shine a little UV light on it, heat it up, and it decomposes. And the way it decomposes is this bond breaks and produces bromine radicals, but at a very slow rate, so that the radicals then create a bromine radical, rather, creates a carbon-centered radical over here. One carbon away from the carbon-carbon double bond, and you get substitution. So the B of NBS means bromine, and so to predict the products, you should do a little mini mechanism, but I haven't shown you the mechanism yet. So I'll do that in a second. But it turns out this is the one and only product you get for this reaction. It's kind of a little fib. I'll show you the mechanism. We'll see that actually 2 molecules are being made, 2 products, but they are in fact the same thing. Okay, so NBS, it is a free radical reaction. So we're gonna look at the mechanism. It involves initiation, propagation, termination. Yep, just like we saw before. And the first step, initiation, requires heat or light. And back when we talked about free radical reactions before, sometimes we put a little triangle underneath the reaction arrow to represent heat. Sometimes we wrote H-nu to represent light. And you know what? A lot of times when you use NBS, we don't even put that in there, but they are required, but you don't have to. If you want to put a little heat or light, you can, but often this just isn't written. Okay, before I show you the mechanism, anything else we need to know? Yeah, if you have more than one allylic hydrogen, you could get multiple products. So for example, let's do this. Where's the allylic? Just a little trigger in my head just went off. Said, wait, do we remind ourselves what allylic meant? When we were discussing how the name alkenes, there were 2 common names we had to memorize involving alkenes. There was vinyl chloride, or the vinyl group, which meant if you had a carbon-carbon double bond and you put one group attached to that carbon that's sp2 hybridized, that was a vinyl carbon. These 2 carbons count as a vinyl group. This is a common name. And then if you had another double bond, but one more carbon away you put on a group, that was the allyl group. So this is the common name of this is allyl chloride. And the way I can remember it is there's 3 L's here for 3 carbons. 2 carbons have to be double bonded together, but then there's an sp3 hybridized carbon that has the extra group, the chlorine in this case. Cool. Back to multiple products. If you have more than one allylic carbon, so if you treat this with NBS, well, here's your double bond, and allylic means 1, 2, 3 carbons. So there are hydrogens on this side. So this is going to be substituted with a bromine. And then 1, 2, 3, hey, there's allylic carbons over here. So these are also going to be substituted. Yep, maybe we'll do this reaction in a second. What else do we need? That's it. I'm looking at memorize the mechanism. Include the resonance structure in your mechanism. You need to do that for full credit, but more importantly, you need to write the resonance structure so that you can actually predict all the possible products that nature will make in the lab. Oh, there's one more thing down here. Back in Key Concepts, Unit 2, Part 2, we talked about the order stability of alkenes. And the simple trend was more groups on an alkene, the more stable it is. So we're going to use that pattern to predict, hey, which will be nature's favorites. When nature makes several molecules at the, several products of a reaction, she doesn't make equal amounts of all those possibilities. She has some favorites. She makes more of the more stable product. And so for making alkenes, and I know not directly making them here, but you start with an alkene and you end up with an alkene. Well, given that this molecule has an alkene, carbon-carbon double bond, nature will have some favorites. She'll pick the more stable molecule, more stable alkene to show up more often. And so what you're going to look for are more groups attached to the alkene. And more groups means more stable, and in this case, more of that. That might be your major product. Okay, enough of the details. Let's see some examples. Okay, well, why don't we just do that one reaction we had before? Let's treat this with NBS. We're going to write the mechanism as one way of trying to predict all the products. And there's a shortcut. I'll show you that too. But here's the long way. You might need this because on the exam, I might ask you for the full mechanism. And so this is what you need to do. First of all, you have to memorize NBS and bromosuccinimide involves free radicals. Free radicals have those 3 steps: initiation, propagation, termination. And that's kind of helpful if you just remember initiation, propagation, termination. Well, that might jar your memory, help you remember the steps. Now, they are going to be a little different in some cases. So compare and contrast from when we did free radical halogenation of alkanes, where we saw initiation, propagation, termination, and there's going to be some similarities and some differences. Here we go. Initiation, that's where you make radicals out of halides. So before we split the Cl2 molecule, this time we're going to split the NBS molecule. So you will need to know the structure of NBS, right? So a pentagon with a nitrogen. You don't have to put the nitrogen at the top. You get to draw it however you like. But wherever you put the nitrogen, on the ring to either side of the nitrogen are a pair of double bonded oxygens. And then we do take heat or light. On the exam, you just pick one. And then this is free radicals, so use the fish hook arrows. This is the weakest bond. So a little bit of heat, a little bit of light, well, that energy will be absorbed to help break this covalent bond into radicals, where one line equals 2 dots, one line equals 2 dots, one covalent bond is 2 shared electrons. One of those electrons goes to bromine, the other one goes on to nitrogen. Fishhook arrows show that motion, right? That's what we do in mechanisms, show how electrons move to represent bonds being broken or bonds being made. So nitrogen's going to get a radical, and bromine's going to get a radical. And I'll put the dot over here. You can put on the bomb if you want, whatever you want to do. I'm missing lone pairs on my molecules. That's your choice if you want to include them. They're not required. Turns out this radical is resonance stabilized. Stabilized. Spelling and printing, yikes. And it's very stable. It doesn't do anything else. There's some side reactions that can occur, but they're not important, at least not for this discussion. So we just abandoned this molecule here. It's just scrap. We'll have to clean it up out of our reaction mixture in the lab, but just drop that. Here's the most important component, the bromine radical. So take the bromine radical, and that's your reagent for the start of the propagation step. Now, before we saw free radical reactions, the bromine or chlorine radical took away a hydrogen off of carbon. Same thing here. The trick, though, is you can only remove allylic hydrogens. So, there's hydrogens at the end of this chain over here, but these hydrogens on this carbon are not allylic. They're not one carbon away from a double bond. But this one is, and there's 2 of them here, right? We only have to show one. There's also another one over here. we are going to get different products depending on which hydrogen is removed. So in our mechanism, we have to show both possibilities. So let's pick off this hydrogen in the second step. I'll pick off this first one in the first step. Use your fish hook arrows. What's going to happen is this covalent bond connecting the hydrogen and the carbon splits. One electron pairs up with the bromine's electron to make a bond. The other electron of this covalent bond just does a U-turn, circles back onto carbon. The H and the Br form HBr. Technically, that is a product of the reaction, but you don't have to write it in because the organic chemist says, there's no carbon there. I don't care. That's a waste product. Let's just ignore that. Okay, what else though? What happened to the carbon? That's the organic chemist's opinion here. Well, it's over here. Cool. Let's do the same thing down here. Just keep things parallel. All right, let's see if I can move. How about I put the curved arrows down here? Just give myself a little more room. And we'll kind of circle around here. One electron goes that way for the hydrogen, and the other electron does a U-turn, sits back on carbon. So the radical's up here. Double bond's right there. Cool. That's your propagation steps. Do you remember back when we did free radical halogenation? There were 2 propagation steps. 2 for each product. So I know we got 2 steps here, but really this is just step 1 of propagation. There's a step 2 of propagation, and that's where, go back and review the other reaction. This radical did something. Here with NBS, it's a little different. All you need to do is show your resonance structures. What we need to do is just kind of explain, hey, how come hydrogens at the end of this chain did not get substituted with a bromine? And the reason why is, if you put a radical here, it can't be resonance stabilized by this pi bond. The double bond is too far away. But if you put a radical allylic, the carbon next to a double bond, then you do get resonance stabilization. So you don't have to draw curved arrows for me for resonance, but technically the pi bond splits. One electron pairs up here to put the double bond on the right side. And then the pi bond has its second electron. We'll just do a little U-turn and sit back here. I have some students kind of think of this pi bond like a door on a hinge. It's kind of hinged here and swings over to the other side. And then the radical swings over to where the pi bond left. And we're going to do the same pattern here. Pi bond, you swing towards the radical, so you're over on this side. And the radical, you go back onto this carbon, because when the pi bond left, you left this carbon without a bond. So the radical is going to have room to go over there. Good. All right, so technically 2 steps, if you will. Make the carbon center radical, and the next step is show the resonance structures. Termination. Pair up radicals. That's what we did before, and that's what we're going to do again. However, a little different here. MBS it's just a mild reaction. You don't get every possible termination product. Instead, you only have to draw the products between bromine radical and these radicals. Yikes, there's 4 of them. Yeah, we got 4 products potentially. So let's scroll over here, and we're going to do our termination step. And there's 4 of them, 1 for every radical. So let's grab this first one on the left, top left. It looks like this. Bring in the bromine radical and pair up the radicals. Just kind of connect them together, and that attaches a bromine to the end of the chain. Cool. Grab any one of the other radicals. We need to do all 4. Yes. Just keep repeating it because we're going to get all 4 of these in the lab. So we're predicting what happens in the lab, and this is what happens. kind of curve those arrows that way. And then on bottom left over here, and then what we got? We got swing, not swing, put the bromine there, pair up our radicals. And the last one, bottom right. Curved arrows. Well, kind of a long mechanism. Ooh, don't do what I did. Where's my pi bond? There it is. Get that pi bond in there. We're making alkenes. There we go. Okay, that was pretty long. We got 4 products here. It turns out, though, we may not have them all. What? What's going on? Whenever you have alkenes and you have to name them, remember you also have to consider cis and trans isomers or E and Z isomers. We need to do the same thing in a reaction. So it turns out wherever we have a trans or a cis, we usually can get the other isomer as a product of this reaction. So let's just run down the list of products here. Is this cis or trans or neither? And we got a hydrogen and a hydrogen on opposite sides of the double bond. This is the trans isomer, which means you can also get the cis. Okay, so if I leave this hydrogen up here, I want to put the other hydrogen on the same side, which means I need to put these 2 carbons down here. There's a cis isomer, and yep, we need to draw that too. Okay, second product we made, is this cis or trans isomer? The answer is nope, because this carbon has 2 identical hydrogens. So what we did over here, that we started with trans, going back up here real quick. This is trans, and I said, well, let's swap the hydrogen in the ethyl group, and we'll make the other isomer. But if you try that same tactic here, switch this H with that H, hey, that doesn't change the molecule. Yeah, because this is neither a cis nor a trans isomer. This is down here. Oh, hydrogen, one's up, one's down. That's trans, so we can get the other one, which is a cis. So I'll draw it that way. What about this one? Yep. So I'll draw the left half of the double bond the same way, and maybe I'll swing this methyl group upward. And now I have 7 products. All 7 products have to be drawn for full credit because these are the molecules made in the lab. Now, as we look at this, and if we had to name them, we'd realize that, hey, these 2 are the same. Yeah, these 2 are the same, right? So, well, let's name it. That'd be the easiest way to see that they're actually the same. Starting from the end of the chain closest to the double bond, right? Prioritize the most important functional group. That's going to get the lowest number. So this is carbon 2, and there's 5 carbons altogether. That's pentene on carbon 2, and then 1, 2, 3, 4. This is 4 bromo. Whoops, I forgot the cis. This is cis, 4 bromo, 2 pentene. And it turns out, if you count from this end closer to the double bond, 1, 2, 3, 4. This is also cis 4 bromo 2 pentene. So if you could see that as you're drawing products and you omit the other product, if it's the same molecule, I don't take off points. Anyways, you can draw all these, and some of them turn out to be duplicates. These 2 are the same. These are both the trans isomer of 4 bromo 2 pentene. Looks like this is unique. Got a double bond at the end of the chain. Nobody else has a double bond at the end. And then this one, yeah, this end would be still 2. The alkene's on carbon 2, but the bromine's on 1. Bromine on 1, alkene on 2, but we have cis trans. Yeah. Lots of products. Oh, some of you might be saying, well, how come you get cis here? What happened? Let's do a simpler molecule, simpler example, just to illustrate that. So, new example. And maybe the question would be, draw products and circle the major product. Meaning I want you to pick out which one nature is going to favor. Which one is she going to make more of? And so that might be how the question will be phrased on your next exam. Circle, draw all the products, all the possibilities, but then among them, circle the one, or maybe there might be some ties. So maybe circle the major products. And maybe I'll put a little parentheses around this because it's possible you only have one product. So there we go. Okay, so how do you solve this? Well, you could do it the long way. Draw all the steps of initiation, propagation, termination. But there's a shortcut. Turns out you only have to draw the carbon-based radicals and their resonance structures. So I call it a mini mechanism. It's not something you, if I ask for the mechanism, you get partial credit if you drew just the mini mechanism. But this question is not asking for the mechanism, it's just asking us to draw the products. So we'll do a part of the mechanism, the part that helps us the most, to predict what products are being made. So in the mini mechanism, first you recognize, hey, the reagent's NBS, the B stands for bromine. Substitute a bromine on the ring or chain. Put a bromine on that carbon somewhere. Where? At the allylic carbon. So not on the double bond, but one carbon away. Hey, this is pretty nice. Unlike the other molecule where there are carbons on either side of the double bond, there's only one carbon on the left. It looks like it might be just one product. Well, no, let's draw out the mini mechanism. So what happens is in the process, actually, I have the step up here, there'll be a bromine radical formed from initiation. They'll remove the allylic hydrogen to form an allylic radical. And I'm just going to draw the allylic radical. So the hydrogen up here, one of them is taken away. Let's draw the resonance structure. So swing the pi bond towards the radical. So this double bond swings to the other side. It'll be here then. And then, hey, this carbon at the end of the chain used to have a double bond. Now it doesn't. That one has to take on the radical. Looking ahead, we can see this double bond is trans. So where's the cis isomer? Turns out I'm going to use an equilibrium arrow here to show that before you even make the radical, you can have this single bond, that's a single bond, not double bond. This single bond can spin, right? Single bonds are free to rotate, double bonds are not. You could draw a Newman projection if you want to go that far back. Remember how we spun everything like the helm of a ship? Things can rotate. So before you draw the resonance structure, or even before the reaction gets started, way up here, this molecule could be in this shape. It's not the best shape. It's not the most stable shape, but it can get in that shape when NBS collides with it and pulls off this hydrogen. Or you could, there's some problems trying to rotate it after the radical's formed. But if you just do it here, you can at least predict the right product. If we just spin this, so the methyl group's pointing up, this is the shape of our radical. And then now do the resonance structure of this where you cannot move atoms. So we moved it here. Now with the double-headed arrow, draw the resonance structure. No more moving atoms, only move electrons. Swing the pi bond towards the radical, go here. Double bond, you lost your double bond up here, so there's a radical. Okay, so we have 4 radicals again. Hopefully you can see or just kind of think it through. These 2 are the same molecules, just different shapes. These are, however, are different molecules. One's trans, the other one's cis. So really there's only 3 products here. Now, if on the exam you don't see that and you think, oh, it looks like there's 4 molecules here, and you draw products from all 4, you get full credit because you just wrote the same correct answer twice. Let's do that now. If what you do is in the termination step, bromine will then pair up with all these radicals. So just copy your radical, and wherever there's a dot, put a bromine instead. And so if you said, hey, I'm going to do it down here too, grab this one, put the bromine here. This molecule is the same as that one. You can name it and find out. Or you could spin it. Just, yeah, spin this carbon, get the bromine and the methyl group trade places. They're the same. But this radical, that's trans. It's a new product. And I'm going to put the bromine that way. You don't have to zigzag it. If you want the bromine pointing up, you can. And then the cis isomer, the bromine is going to be off the end here. So yay, I'm going to get lots of points for drawing all the products. We got all 3. If you weren't sure, you could draw this one in there too and still get your points for drawing products. But now let's circle the major product. And the way that works is you need to find the alkene with the most stuff hanging off of it. And so what you can do, as a little memory aid, is to circle the double bond. So I'm changing pen color. So just circle the double bond and see if you cut a single bond. And I just did right here. So as I circled the alkene, I cut a bond. This has 1 group on the double bond. The chemist would say this is a mono-substituted alkene. That's okay, but this one's better. Circling that double bond, I cut single bonds twice. This is di-substituted. 2 groups are on double bond. Nature says, yeah, that makes a better and more stable alkene. I think I'll make more of this one. What about circling this one? She says, ooh, that's also di-substituted. They're both di-substituted. So nature's going to make more of both of these. There's also a tiebreaker though, right? Who is more substitutes? Who is more stable? Sorry, who's more stable, cis or trans? Trans is more stable. It's roomier. Here the hydrogens on the methyl group are crowding out the hydrogens from this carbon. But here the groups on hydrogens on this carbon, bromine and hydrogen on this one, they're farther apart. That makes it more stable. Switch back to another color or erase your work. Be a little careful on the exam. It looks like I've circled everything. So maybe I'll put a big box around it on the exam and say, okay, Dennis, this is the major product. Or maybe you just write the word major here. Make it totally clear that nature's going to make more of this one, not so much of the other 2. Nice. Okay, NBS is going to show up quite a bit this semester and next semester. It's going to be useful for taking an alkene and putting a bromine on it and doing other things with it. All righty. What else we got? We got the pen fixed back. We do. Let's take a look at the next reaction. Well, that's it. I am out of order here. No, I'm just getting confused. We're trying to make alkyl halides, and so there's another way of making alkyl halides. Sorry, need more sleep. You can start with an alcohol. That's what this is saying, and you can make alkyl halides from them. Just need to read what's going on here. Well, let's take this molecule that has an alcohol on it and say, hey, I don't want that OH group anymore. Let's put a halide on there. Well, how about HCl? Put a chlorine on there with hydrochloric acid. And yep, make the swap, put a chlorine. Someone else says, nope, bromine's my favorite, so I'll use HBr. And wherever the alcohol is, you get a bromine instead. The trick though, it really only works best if your alcohol is tertiary. Remember how that works? Hey, alcohol, what degree are you? Primary, secondary, tertiary, or quaternary? And the alcohol doesn't say anything, it's shy. So go talk to the carbon it's attached to. Hey, carbon, what degree are you? And that one says, oh, let me check. I'm attached to 1, 2, 3 carbons. Oh yeah, I'm tertiary. And that makes the alcohol tertiary also. If you have a secondary or a primary alcohol, you might get a carbocation rearrangement, or you may get no product at all. Sometimes the carbocations just won't form. So this is a big red flag. I try to avoid using these reagents unless they're tertiary, because these are cheap in the lab. Every chemistry lab is going to have a little HCl somewhere. So you can do this reaction pretty easily, but it only works best if you have tertiary groups. Memorize the mechanism. It's actually not too bad. Let's shake it up. Let's add HI. So maybe you want iodide instead. And remember these reagents also make hydroiodic acid too. So you can use phosphoric acid and potassium iodide and get the same alkyl iodide product. Here's our mechanism. Doesn't have to be iodide, it could be bromine or chlorine. But it's an acid, HCl, HBr, HI. Acids donate hydrogen. That makes the alcohol group a base. It's going to accept specifically with its lone pair. So the oxygens, one of the oxygens lone pairs will make a bond to H+, iodide, or whatever halide is attached to, will then grab the extra bonding electrons and make it a new lone pair. And then we get something that we might call a protonated alcohol. Protonated, yeah, it's got an extra proton on it. Remember, H+ is hydrogen with no electrons. It's simply a proton. If you want to put an H on this side, so you write HOH, full credit. When you're drawing it, you decide how you want to draw it. You also could put a 2 right after H. That's fine too. Hey, but whoever's drawing it gets to decide. I like putting my H on the other side with a 2 because that looks like water. And that totally helps reminds me what the next step is. Water is really stable. It just wants to break away on its own. And that's what happens in the lab. This carbon used to have 4 bonds. It was happy, but the water molecule took off because that's a nice stable thing. And oxygen gets 2 lone pairs, 2 covalent bonds. It's nice and stable. This poor carbon, though, is now a carbocation. It's tertiary. And the tertiary carbocations generally do not rearrange. So that's why tertiary alcohols are best for this reaction. Last step, opposites attract. So drawing a lone pair on that anion, go attack the cation. Plus attacks minus, minus attacks plus, whatever. And then where the alcohol used to be, we get substitution with your halide, this time iodide. And we're done. The chemist comes along and says, yeah, I want halides out of my secondary alcohols and out of my primary alcohols. How do I do that? Well, this reagent doesn't work so well. So switch reagents, that's how you do it. These are the 2 that are most common. If you want chlorine, use thionyl chloride, SOCl2. It looks like this if you want a structure. Thionyl chloride is the common name. Phosphorus tribromide, well, that one's pretty easy. Phosphorus in the middle, 3 bromines. Cool. You don't get any carbocations in the mechanism, so there's no rearrangements. It works on any alcohol. Well, doesn't work that great with tertiary, but we're gonna let it slide. So if you wanna make a halide on the exam, these will be the safest bets. Use PBr3 or SOCl2 to change an alcohol into a halide. And you don't have to worry about being a, whatever degree alcohol. You don't have to classify it. Just go ahead and crank it out. Just draw it out. So we start with the same alcohol as before. You want bromine, PBr3 will work. If you want chlorine, use the other one, but hey, maybe you want to take this alcohol and turn it into a chloride. HCl won't work here. It just doesn't work well at all. And you have to heat it up. Things will boil and evaporate. You don't get very good yields. But thionyl chloride works pretty well. Whoops, thionyl chloride in my head. There's no S in the product. This is organic chemistry. Where's the carbon? There we go. So substitute the OH group with the chlorine or the bromine, depending on which reagent you have. And again, my guideline is, well, memorize the mechanisms that are helpful, like that silly NBS reaction. There's so many products. We need a method to generate all the possible products. And that's by writing out at least a mini mechanism. But here, let's wait. The pattern is substitute the OH group with bromine or chlorine. You really don't need the mechanism. It's known. If you want to look it up, you can. But I don't find it useful for predicting products. So I don't require students to memorize it. And most textbooks don't even include it in their books. What else we got? Yay, we're done making alkyl halides. So we synthesize a bunch of alkyl halides. And now we're going to take those products and use them in another reaction. So let's take the alkyl halides we just made and do something with them, change them into other functional groups. Okay. Lots happening here. So the first reaction I'd like to go over is something called the Grignard reagent. And the actual product you get out of here is pretty boring. We're going to have the Grignard reagent react as a base. Next semester, we'll use the Grignard reagents to do some really powerful chemistry on carbon-oxygen double bonds, aldehydes, ketones, esters. But those functional groups don't show up the next semester. However, most textbooks are like, wait, we're talking about alkyl halides right now. You got to at least mention the Grignard reagent. So, okay, let's mention it. So start with the alkyl halide, whatever. My favorite halide is bromine, but yours might be chlorine or iodide. Fluorine doesn't work well. Keep remembering that Teflon is made out of fluorine, carbon and fluorine, and doesn't stick to it. The reaction doesn't stick to fluorine. Yeah, most reactions don't work well with fluorine as a halide. So chlorine, bromine, iodide works here. And you add magnesium metal. That's your reagent. Don't put a +2 here, because that means it's not the metallic elemental form. You could put a little subscript S if you want, or don't. And what's cool is that magnesium atoms insert themselves between the carbon and the bromine. It's a redox reaction. We're not going to go over the mechanism. And then after the reaction, the research shows that the carbon to the magnesium should be ionic. Carbon's a nonmetal, carbon's a nonmetal, magnesium's a metal. And when you have a metal to a nonmetal, we usually predict ionic bonding. But the properties of this molecule are such that it acts more like a covalent bond. Now, normally we saw magnesium last semester in Gen Chem forming a +2 cation. So it likes making 2 bonds. And that's still true here. It's just that magnesium is going to make 1 covalent bond to carbon and 1 ionic bond to bromine. And so technically magnesium is a +1. Most of the time we don't even write the charges. We just write the Grignard reagent like that. So I'll put that in parentheses saying, hey, that's what's actually happening with the charges, but we'll just draw the product like this, and this is called the Grignard reagent. It's characterized by a carbon to magnesium bond. What's special about that? Well, let's go back over here and say, hey, who's more electronegative, carbon or bromine? I should have posted a periodic table, but if I write part of the periodic table, let's see, boron, carbon, nitrogen, oxygen, fluorine, neon, and then it's chlorine and then bromine down here. Remember the trend? The closer you are to the bully, fluorine, the more electronegative the element becomes. So oxygen and chlorine are very electronegative. Nitrogen, bromine, less so. Carbon, even less electronegative. Bromine is 2 steps away from fluorine, but carbon's 3 steps away. Or in other words, bromine is more electronegative, so it tugs on these bonding electrons more than carbon pulls back. So carbon's slightly positive, bromine slightly negative. What about the carbon-magnesium bond, right? So the research says that's a covalent bond. Is it polar covalent or is it non-polar covalent? Well, where's magnesium? It's way over on the left side of the table, even farther away from fluorine. It is not electronegative at all. In fact, it likes to release electrons, electropositive, if you will. Carbon is more electronegative than magnesium. So this what makes the Grignard reagent special. We have a change of charge. Carbon used to be slightly positive, and now it's slightly negative. Cool. Let's see, did I miss anything? We use solid magnesium, got alkyl halides. Oh, what degree is this alkyl halide? We'll talk to the bromine. Hey, what degree are you? Primary, secondary, tertiary, or quaternary? He's shy. Okay, so talk to the carbon. Hey, carbon, how many carbons are you attached to? And this carbon says, I'm just attached to one carbon, I'm primary, which makes that a primary halide. Turns out Grignards are not selective, they don't care. You can have any alkyl halide, tertiary, secondary, or primary. You can also have an sp2 hybridized carbon. So that's a bit unusual. It's no longer an alkyl halide, right? Alkyls comes from alkanes, single bonded carbon. So this functional group, if you will, where there's an alkane and a halide involved in the same carbon, that's not an alkyl halide because this carbon's not an alkane. It's an alkene. Well, maybe we'll use the common name. It's a vinyl halide. Aryl, remember that? That's another name for the arene group or the benzene group. If you put a halide on that, that'll work too. You can make Grignard reagents out of this as well, even though it's not an alkyl halide. Okay. Carbon's not happy for this last point. Water as the acid. What's that all about? Carbon, we just said, is not electronegative. It can't handle this negative charge. It's freaking out. Someone take away this extra negative charge. One way to do it is to go quench it with something positive through an acid-base reaction. So if you have any water around, I mean, literally, if you breathe on this, the moisture in your breath will react. If you just leave the beaker of the Grignard reagent open to the air, there's moisture, humidity in the air, and the water in the air will react. This Grignard is a super powerful base. Carbon just cannot handle the negative charge. And so carbon says, I'm gonna go steal this H+ and make a covalent bond to hydrogen. See you later, magnesium. And so you do a substitution reaction. The carbon ejects the magnesium bromine. It actually takes this bond of electrons and grabs H+, strips it away from water. Remember from general chemistry, water is a weak acid. Well, the Grignard is such a powerful base, they'll take it and, hey, I already drew the product. But if you want to emphasize there's now a hydrogen where there used to be magnesium, you can. If you like byproducts, then you have an Mg2+, because this bond got used by carbon. It's a more electronegative than magnesium. So the bonding electrons were taken by carbon. So now magnesium was +1, now it's +2. Bromine's a spectator. It's just hanging out with the cation. And what became of the water molecule? Well, when H+ leaves, water turns into hydroxide ion. And there's no carbon here. So the organic chemist says, that's waste product. But it's a mixed salt. Magnesium has two different anions, but it all combines to neutralize the charge. Cool. There you go. And this last step is an acid-base step. This is the acid, the Grignard is the base. There's some key points down here. Drawing the resonance structure of the Grignard reagent helps us see the negatively charged carbon. Negative carbon is called a carbanion, an anion of carbon. I'll show you that in a second. And then here's the emphasis. This semester, we're only going to talk about how Grignards act as bases, but next semester, we'll make new molecules with them where they act as nucleophiles. They seek positive charge, right? Phile means seeking or loving. Nucleo refers to the positive nucleus. So Grignards want to seek something positive. We'll see that next semester. Mechanism. Yeah, let me show you the resonance structure of the Grignard. So if I said, draw the mechanism. And I said, okay, whoops. I'm trying to make something up in my head. Let's draw this molecule plus, I guess I'll keep using water. Nothing special about water. It's just all over the place. It's readily available, but you could use HCl as your acid. If you want to get fancy, oh, maybe we should get fancy. Let's get fancy. Let's use heavy water. So swap out the hydrogens with deuterium. That is hydrogen, but remember the hydrogen that has an extra neutron in it is twice as heavy as hydrogen. We actually have ways in the lab to actually track the deuterium. So we can label the deuterium with the letter D, it's hydrogen. D2O is still water, still weak acid. What do? It's substitution. But let's show the mechanism. And one way to show the way the reaction goes is to actually draw the resonance structure. It's not required, but you can. What you do is you take this bonding electrons and give them to the more electronegative atom. You give them the carbon. And now carbon has a net negative charge because it has a lone pair. That magnesium is then a normal +2 cation. Chloride is a -1 anion. And there's the resonance structure. That's the resonance structure of your Grignard. And that's a little more, for me, it's a little more satisfying because magnesium is a metal. When attached to a non-metal chlorine or a non-metal carbon, it should be ionic. And hey, I see charges, these are ions. Now let's write out the water molecule with deuterium and say, hey, lone pair, go grab your D+, your H+, the acid, and then these bonding electrons fall back onto the oxygen. And now you have a deuterium atom where there used to be a Grignard reagent, the magnesium. And if you want to, it is a mechanism, we probably should. We should show the waste product. This used to be like a hydroxide ion, OD instead of OH minus. And then there is some Mg2 plus and some Cl minus. There you go. Nice short mechanism. Yeah, much shorter than allylic bromination with NBS. Gilman. Okay. The Gilman reaction, or also known as the Corey-House reaction, also effectively called the Cooley reaction. We're going to spell Cooley like this. I just call it that, or you can call it like that, but don't publish a paper with that. No one knows what you're talking about. Okay, how does this one work? Well, this is another reaction using alkyl halide. So go grab an alkyl halide. Do we have to worry about whether it being primary, secondary, or tertiary? Nope, any of them work. And again, the vinyl halides and aryl halides work too, just like in the Grignard reaction. Okay, what do you do first? Add a little lithium metal. So not a plus, I know it's an alkali metal, it likes to be positive, but we're gonna go for a reagent that's elemental, the original lithium metal. And what happens? Well, it does the same thing as magnesium metal does. It inserts itself. The problem is lithium is right above sodium and potassium. They only like making one bond, and that's a bond to the carbon. It can also bond to the bromine. If you want to balance your equation, which I do not, I'm an organic chemist. We kind of don't do that unless we're in the lab and we have to do some stoichiometry. You actually need 2 lithium atoms for every 1 alkyl halide. 1 lithium goes to carbon, the second lithium goes to the halide. You make lithium bromide. Li plus would be R minus. But we're gonna just leave that out. Then what do? Next, you add some copper 1 iodide, or just CuI. And the copper inserts itself between the carbon and the lithium. But copper can make 2 bonds, and it does. Okay, so copper connects to this 3-carbon group wherever the lithium currently is at. So that's the same point of attachment. But copper wants 2 bonds. So it's going to go grab another 3-carbon group, another propyl group, and connect it to the other side. 1, 2, 3. It turns out that, well, let's ask the question, who's more electronegative, copper or carbon? Copper is a transition metal in the middle of the table. Carbon's a nonmetal on the upper right. Carbon's closer to fluorine. It's more electronegative. So it's actually slightly negative, slightly negative. This is slightly positive. If we draw the resonance structure, then we make these carbons negative. We make them carbanions. And then what's the charge on the copper? Let's ask ourselves, what do we start with? Copper 1, there it is. Remember your Roman numerals tell you the charge. Or if you just had the chemical formula, you could predict copper's charge based on iodide. Iodide likes to form a -1 ion. If this is a neutral salt, stable salt, and it is, the copper must be +1. Okay, wait. This molecule is covalent, but the charges are still there. You might call them formal charges. They're not balancing. Yeah, there's 2 minuses, only 1 plus. So this lithium is going to hang out and balance the charge. So there's another lithium ion here to balance the charge. This is the Gilman reagent. It's a copper-based reagent. It's an organocuprate, if you really want a fancy word for it. Maybe you don't. And most of the time, we take a shortcut in writing it, right? So start with the alkyl halide. I randomly pick 3 carbons. You could have a different number of chain of carbons. It could be a ring of carbons, because any works. I start with 3, so then I attach the same 3 to lithium. You could also attach the same 3 to copper with the lithium, and you put a little subscript 2. And these 3 drawings all represent the same Gilman reagent. And now this is the Culi. Culi? C-U-L-I, if you try and say that, then Culi. Anyways, that's usually how I draw my Gilman reagents. I put the set of carbons I start with in parentheses with a little subscript 2, attach it to C-U-L-I, and that represents the Gilman reagent. And then finally, what do you do with this? This is the cool part. There's some limitation. You cannot use a secondary or a tertiary alkyl halide. You need to use a methyl halide or a primary halide. You could use a vinyl or an aryl halide. Really won't see too much of that this semester. So I'm just going to pick, how about a methyl halide? Bromine's my favorite, but chlorine works, and iodide. What about fluorine? No, fluorine's Teflon. No, doesn't stick, doesn't work. And you do substitution. So wherever the copper is attached, that's where you attach all these carbons. So if you had a long chain, let's put 4 carbons here and put a chlorine. Then wherever the halide and the copper attach, that's where you link them together. Okay, let's make this branched here. So this carbon is primary, so it works. There's a primary chloride. So connect this carbon to this one. How about I flip it around? So these 3 carbons are those 3. These 5 carbons, 1, 2, 3, 4, 5. Yep, are those 5. And you link them together. That's the product. Do the same pattern up here, 3 carbons, and then you have a methyl, link them together. And if you draw it that way, full credit. But if you want to draw it like that, full credit too. That's the Gilman reaction of the Corey House, or affectionately called the Cooley reaction. Yay. Let me check my notes, see if I forgot anything. There's no mechanism. I did forget to mention that, but it should be in the notes. Let's look at the notes. Organocuprate. You don't need to know. It's not underlined, so it's just interesting information. They are very strong bases, right? Because we got that carbon that's acting like a carbanion right here. So if your glassware is wet in the lab or you breathe on this, it's going to do an acid-base reaction instead. It's not going to link your carbons together. So you got to be very careful in the lab doing this reaction and keep moisture away. Tell my students, if you clean your glassware before using it, you actually dirtied them up by wetting them with water. Water is going to inhibit the reaction. It's going to do a side reaction. Yeah, watch out for acid-base side reaction. More on next semester, so don't worry about that so much now. No mechanism on the exam. Yay. Again, don't really need it to predict the products. Hey, and this is a key point. The Gilman reaction makes bigger molecules. So we can actually synthesize something from small pieces, right? So can I fit the whole thing on the page? Kind of. We started with 3 carbons, and then in the end, we connected 3 carbons to 5 carbons and made an 8-carbon molecule, a bigger molecule. And just like the extension of terminal alkyne reactions, right? Remember that one, take a triple bond, an alkyne. This is acetylene. Treat it with a strong base, NH2, sodium amide. Pull off one of the hydrogens at the end. There's a hydrogen on either end of the triple bond. And then you also have to add a primary or methyl halide. Can't use secondary, tertiary. But we could use this one too. This is a primary halide. And the triple bond connect where the chlorine currently is. So those carbons, I put a little dot there in my mind. Okay, remind me that's where you connect the triple bond. Yay, and that also makes a bigger molecule. So these are great molecules for doing multi-step synthesis, retrosynthetic analysis, figuring out those pathways. And these are 2 popular reactions on building up bigger molecules. And of the 2, it's preferable to do the alkylation of terminal alkynes, because your final product has a triple bond in it, and you know some triple bond reactions, and you can keep building. Whereas the Gilman reaction, or Corey House reaction, usually end up with an alkane, and that's a dead-end product. We really don't know how to change alkanes into something else. Basically, alkanes, we can do the combustion reaction. You'd burn them. That's not so useful synthetically, if you want to try and make an interesting molecule. Cool. Hey, the last reaction for this video, last reaction for this mishmash of alkyl halide reactions. This one's called the Suzuki-Miyaura reaction. I'm sorry, I'm not exactly sure how to pronounce that, but 2 guys found this cool coupling reaction, it's called. Take 2 big benzene rings and you link them together, and that's really useful, making big molecules. It's also an introduction to palladium chemistry. So if you take more chemistry after this 1-year sequence of organic chemistry, you'll see a lot of palladium chemistry. It's very popular. Palladium does some really cool stuff, and palladium has low toxicity, so you can use it in reactions and try and purify the palladium out of it. But if you don't get every last bit, it's okay. It's a very popular, very useful. So I think that's why it's showing up here. I'm trying to make a case for it. Why am I making a case for it? Well, in the first year of organic chemistry, I mean, you and I, this semester and next semester, we really are not going to use this, because here's the reaction. You have to start with something called a boronic acid, which we haven't figured out how to make yet. So magically, it's going to show up here. It's going to be boron, and it's going to be a benzene ring that's also called the aryl group. You could also have a vinyl group, carbon-carbon, double bond, or a benzene ring, aryl, and then you connect it to boronic acid, which is boron with 2 OH groups. Unsubstituted boronic acid has 3 OH groups. You might see it drawn like this. Say, hey, there's boron with 2 OH groups, 2 OH groups, and a vinyl group or an aryl group. And then you bring in the second molecules, any aryl halide or vinyl. And oddly enough, this whole unit 3 involves alkyl halides. Nope, Suzuki-Miyaura reactions don't use alkyl halides. Chemistry, exceptions upon exceptions. Okay, so bring in your favorite halide. Hey, mine's bromine. And connect it to a benzene ring or to a vinyl group. And you get set to couple these benzene rings together. Wherever the boron is, wherever your halide is, those 2 carbons will then connect together. So this benzene ring on the left will connect to this benzene ring on the right. You connect these together. The reagents that are used to do the coupling reaction, the Suzuki-Miyaura reaction, is tetrakis triphenylphosphine palladium. You abbreviate it as PD that's palladium. Then another P for phosphorus with 3 benzene rings, which have the common name, which is an accepted IUPAC name of phenyl. So phosphorus with 3 pH groups. And there's 4 of these phosphoruses with 3 benzene rings, all stuck on the palladium. I'll draw that in a second. You don't have to memorize that structure. I'm not going to be drawing it on an exam. There's too much. You will just need to recognize this chemical formula. Recognize that there's a boron, not bromine, boron attached to a carbon, and that's going to identify the Suzuki-Miyaura reaction. You need a little calcium carbonate. Sometimes THF is listed here, but that's a solvent. It's not required. And those are your reagents. I promised drawing out the palladium, tetrakis, whatever thingy. So this is the way it works. We're going to get 4 phosphorus atoms. They have lone pairs. Phosphorus is in the same family as nitrogen. Nitrogen likes 3 bonds and it has a lone pair. So it turns out the phosphorus atoms use their lone pairs to connect to palladium. You could just draw covalent bonds if you want. Coordinate covalent bonds, if I remember my Gen Chem. And then these have 3 benzene rings attached to them. And yeah, we might be drawing this all day. You think with so much practice, my hexagons would get better with time? Shortcut is just write the pH3 group, or that's a better shortcut, just write pH3. And then, I know, I cheated. That's sort of the structure. If you want to see the full-blown thing, drawing all your C's and H's. What a mess. What else do we need to know about it? 2 benzene rings connected together are called a biaryl compound. It's not underlined, it's just interesting. Oh, but this is important. Wherever the boron and the halide used to be is your point of connection. And there's no mechanism on the exam. Oh yeah, and if you're gonna major in chemistry and plan to take more organic chemistry, I already mentioned, you're gonna see a lot of palladium catalyzed reactions. Let's do another example. Let's predict the product. And I might put a little subscript S and let you know that there could be 1 or more products. You got to remember the reaction, be able to predict it. How about we draw this molecule? And then that crazy palladium pH3 with an outside 4 and calcium carbonate, limestone, also found in seashells. You want to put THF, you can, not required. What's the product? So I would give you all this. That would be the format of the exam question. What do you do? First, you have to recognize, oh, there's boron. Oh, there's this palladium crazy molecule. This is the coupling reaction, the Suzuki-Miyaura reaction. And wherever the boron is attached and where the halide, iodide's a halide, that's your point of connection. So copy everything else. So starting on the left side, I'll copy the benzene ring with a methyl and a tert-butyl group. And the boron used to be here. It's gone now, it's substitution reaction. And then I got the other benzene ring where the iodide used to be here. And the isopropyl group is over there. And then just connect them together. That's your product. Very cool, huh? All righty, we've covered a lot of ground. The last part of Unit 3 involves a whole set of reactions. Sorry, grab the cursor, move things over. Yeah, reaction number four. It's a whole set of reactions. They're best described by looking at their mechanism. Yeah, there's a whole separate key concept to cover these. These might be the most important reactions in all of organic chemistry. It's pretty high up there. So we'll spend some time talking about Sn2, Sn1, E1, and E2 reactions. The subscript E stands for nucleophilic, hence the meme. E stands for elimination. S stands for substitution. That's just a quick little preview, but take a look at the next video if you want to learn more. Next couple of videos, actually. All righty. Take care.